Hi everyone, thank you for joining. So in the last video we defined simultaneous events to be two events, E1 and E2, which takes place in different position in space, but they occur at the same time. That was the definition of simultaneous events, of course measured by some reference frame, right? And in this video, we're going to look at a paradox, and the aim of this paradox is not simply to confuse ourselves, but to understand what does simultaneity means in relativity, to have a better understanding of simultaneous events, right? So we have this little thought experiment. What we have here is that we have a little car, and on the car there are two detectors and one person, and there is another person on the platform observing this, right? And the car is traveling with some velocity v, right? Constant velocity v. Okay, so the rules are this. So there are two firecrackers at K and at M. So one firecracker at K and the other one is at M. And they explode. And once they explode, the light will be traveling spherical in every direction. And if the flash of light reached the light detector first, in other words, if the light from here reaches the light detector first, the observers will see green light flashing from this detector here, right? And the second rule is that if the light reaches to the left from K first, or if light reaches from left and from right at the same time to the detectors, observers will see red light. Okay, so that's the rules of the game, right? Okay, now let's have a look at what the person at A will observe, right? Okay, so if you look at it, at this first picture, we have the firecrackers exploding. And once the explosion has taken place, the light starts traveling. So let's add some light waves here. So light is, let me get some dashed line from here, there, and then from there. Okay, so let's say light has traveled from M to, that should be M here and K there, to this point, right? And the light on the left from K will have also traveled some equal distance there, right? Okay, and then because the card is moving, what will happen is that the light will travel further down from right here, and from left it will have traveled there, right? And I will put a right in between. Okay, so this is how the events are observed by person standing at A. So according to the person standing at A, as you can see, you can, like, geometrically as well, this will be an isosceles triangle. So it is not surprising that for person at A, these events are simultaneous. Yeah, so these events are simultaneous. So the light explosion takes at the same time and reaches the person at the same time as well. So the person A will deduce that these events are simultaneous, right? Okay. So, but more importantly, if you look at it, this light wave here, yeah. Now, what's going to happen? Well, that means the green light will flash, isn't it? Because that means the light from M, from right, reached the detectors first. Excuse me. So that means the person, let me write that down, person at A will see green light. Yeah, okay. So person at A sees a green light, but now let's have a look at the reference frame of the person B. So what will person at B will observe is that the two firecrackers exploding at the same time. So what will happen is that the light waves will start approaching the detectors from right and from left. And then we have this point here which you see two light waves approaching the detectors. And what's going to happen for the person at B, the person will receive that the both light waves reach from left and from right, reach the detectors at the same time. So in other words, we will get red light here. So that was the rule, yeah? So in other words, the person at B will observe red light. Right? But then let's say the experiment finishes and person A and person B gets together and they want to see the box. So how can that be that the box will have both green and red light? These are mutually exclusive, isn't it? Right? So yeah, so this is a paradox. So if you want to think about it a bit and then well, pause the video and think about it, and then we could go over it. Okay, let's resolve this mystery. So the right way to think about it is for a person at B, observer at B, firecracker on the right must be exploding first. So what happens is that it explodes at the first, and then the light wave starts traveling towards the detectors from there, and then you have explosion on the left where light start traveling, but then of course this here would have reached the detectors first, so the both observers will see green light, right? So that's the crucial thing about the simultaneous events in relativity. Yeah, so the right firecracker must explode before the left firecracker in the frame reference frame of B. Yeah, so the assumption that both firecrackers exploded at the same time from as seen by B was incorrect, and this is in fact the whole point about, I'll write it, relativity of simultaneity. Yeah, if you have a simultaneous event observed from some reference frame, and there is another reference frame which is traveling at some velocity relative to the first one, it will not be simultaneous there. Yeah. So I'll say it one more time before I end this video. So the idea here is that the two events occurring simultaneously in reference frame S, let's say, are not simultaneous in any reference frame S dashed that is moving relative to S. And this is the relativity of simultaneity. Okay? If you think about this paradox deeply, you will realize that actually the only way to resolve this paradox is to give up the idea of the measurements made by B was the events took place simultaneously. Anything else will lead to contradiction. Yeah. So this is the only plausible explanation to what is happening. Okay. Well, in the next video we will look at time dilation, which is really interesting, I think, because we get to learn the property of time. Okay, so I hope you enjoyed it. I hope you found it interesting, and I look forward to seeing you in my next video. Thank you.